Good. Oops. So, and now you see the wrong view again, is that correct?
Of course, yeah.
Of course you do. At least it's reproducible.
Yeah. No, it's good.
Okay. Dear Thomas, dear Maxime, thank you very much for putting CMDS online. The show must go online these days, and that's great. I think it's especially good for students. And I'm very happy to contribute to this lecture series. And I'm also happy to be part of this CMDS community. It's always been one of my favorite conferences. So I would like to give a monothematic talk now, the experimentalist view on R5 spectroscopy on fifth order 2D. What do I want to achieve? I would like to convince you that fifth order 2D is an interesting approach. It is especially useful when you're interested in Exciton-Exciton annihilation. This goes so far that, let's say, the inventor or the guy who realized R5 the first successful R5 experiments, Tobias Brixner, calls it EEI 2D, so Exciton-Exciton interaction 2D spectroscopy. But first, a little bit about the people behind this. This work heavily, like most 2D spectroscopy, heavily relies on theory support. And when you go for higher order interactions like fifth order, you better have a good theory team ready to understand what you're doing. And our main collaborator is František Šanda in Prague. And he, to a large part, supervised Konstantin down here, who did all the theory plots you will see in the following. We also had some support by Felix Plasser, who's in Loughborough now, and Maximilian Menger, who is not far, from you guys, he's in Groningen, and they did quantum chemistry for us. The samples were provided by Christoph Lambert, which for those of you who know him, yes, we used squarings and we enjoyed them immensely. Now, here's for a short outline. So first of all, as I mentioned, this is basically a technique that is, in my opinion, tailor-made for looking at Exciton-Exciton annihilation. So I'm going to say a few introductory words on what I mean by that and how we interpret this complicated process. And then I will show you the new approach. It's relatively new, let's say. Fifth order 2D electronic spectroscopy and how it helps to understand Exciton-Exciton annihilation dynamics. And then to a fairly large part, we will go into details and discuss an example of this method and how it's useful in understanding the Exciton-Exciton interactions in a trimeric system. But first of all, if you're not an expert, what is annihilation? We start with a very simple system here on the top left. It's two molecules, both of which have 3 electronic levels, and they sit right next to each other, and they carry 1 excitation each. So each of them is in an excited state. So obviously this here is already a description of a doubly excited state. Now, when these 2 excitons are on neighboring sites, they start to interact, and then interesting things happen. So this is the step number 1 here is sometimes called exciton fusion. So 2 singly excited state become 1 doubly excited state, like 1 F state here, which I should say. Other people have called it exciton localization, which is also a fitting term because here you have 2 excitons right next to each other. And then you localize the exciton on one of these molecules. So you have now 2 excitations sitting here. So you put the excitation here in this doubly excited state, while the other one goes back down to ground for energy conservation. Now, this here is a localized state. This is fine, but it's not going to be very long-lived because, well, this is a very high-lying state. So you will need to also consider relaxation, non-radiative relaxation in this case, back down to this E state, this first excited state. So Exciton-Exciton annihilation is a process in which you get rid of 1 exciton. 2 excitons here become turn into 1. So basically, it's something you don't want in most cases. For example, if you're building a thin film organic solar cell, this is something to avoid. However, people now, as 2D materials become more and more fashionable, people also have considered ways of utilizing this. So when you have this type of relaxation, you might also end up with a vibrationally hot state, so to speak, and you can harvest them as well. So there's not only downsides to it. And of course, if you're interested in natural light harvesting systems, also artificial ones, then if you study Exciton-Exciton annihilation, you will get information about the energy level scheme you're looking at. So it is a way of probing the system. And some consider it even a protection mechanism for high intensity radiation, but this is a matter of debate. Now, what we do when we treat this theoretically is a phenomenological approach. So we, as soon as we have two neighboring excitations, we have this operator here, this annihilation operator, which is connected to a rate that then leads straight to this situation. So we don't really talk about this fairly elusive process of exciton fusion, but we go straight to this state after the relaxation. So what we do here in this operator is we deplete this F state and also the first excited state. So basically, it's a unidirectional relaxation of these states. So this was already enough theory for my taste. Now, here's a quick example, which is not multidimensional yet, but it's still worth mentioning, not least because our hosts here are big fans of this type of system, J aggregates. I even mentioned this very recommendable paper of theirs here, where they look at Exciton-Exciton annihilation in a tube-in-tube system. So this is they look at a double tube, which makes things more complicated, gives you different regimes of annihilation. This here, what we looked at is a monotube. This is a single tube made of TDPC, that's the name of the monomer. And it's only 4 nanometers in diameter, but micrometers in length. And the interesting feature here is that in this double tube system, the molecules were sort of stacked edge to edge. But here, as you only have 4 nanometers in diameter, then the molecules will actually be pi stacked. So pi system is on top of pi system, which gives you a J-type interaction, head to tail, but also H-type interaction, because the pi systems are on top of each other. And accordingly, you have a J band and a H band in this system, and they're differently polarized. So everything is as you expect. It's not the most stable system, I should say. It's a bit precious, but very interesting because it's still a monotube and you can work with it under the right conditions. Now, if you do a fluorescence measurement, a very simple measurement, you just excite at either the H or the J band, then you will see that your fluorescence intensity may get less when you hit it too hard. So when you normalize to fluorescence yields of just number of photons that come out for low intensities, you get a value which is fairly constant, and then it goes down rapidly. Now, the interesting thing is that, of course, this is of course a sign of Exciton-Exciton annihilation and many other things. So when all you have is this, it's a bit tricky to get the right parameter range out, to be honest. Now, but we have another hint that Exciton-Exciton annihilation in this system is actually something omnipresent and defining, because if we pump at 600 nanometers, which is just the peak of the J band here, then already at very early times, 200 femtoseconds, we see excited state absorption that sits above the H band here, right? So this would tell you that you populate the J band and then something puts population in the H band automatically, right? So this ESA here can only be explained by ESA from an excited H band over there. This is interesting, and the model that we have to explain this is that Exciton-Exciton annihilation is extremely efficient in this type of system. So you put population here in something which is at twice the energy of the J band, and this doubly excited state here transfers efficiently to the H band. And this explains this ESA, which we actually were never able to get fully rid of, even if we excite with very low excitation densities. So this is just an example of how Exciton-Exciton Annihilation will let you say something about the energy level structure of your system and the dynamics connecting these levels. And it also tells you that the rates of this are pretty hard to determine. Now, what do I mean by this rate? The only rate that we have here is basically the relaxation from the double excited state back down after this exciton fusion process. Now, so ideally, you would have a method that lets you determine the rate of population relaxation from this double excited state back down. And ideally, you could do this at a single excitation intensity, because intensity dependent measurements generally come with their own set of problems, as it's written here. There are many things that can happen when you excite your system very hard. I'm not talking about ionization or anything brutal like this, but there's a multitude of problems, especially with precious systems that you can hit. So ideally, you would have something that works at low excitation energies, and you only need one intensity to scan. So here's a already established solution, let's say, to this problem. So again, we look at this process here, Exciton-Exciton Annihilation, and we are especially interested at the rate of transfer between this F state and back down to E, because that's hard to determine with other methods. In this paper by Brüggemann et al., out of the group of Töne-Pulleritz, they suggested this phase matching condition. We will see that this does exactly that. It populates this state, and then you can look at its decay without the need to do intensity-dependent experiments. As I also mentioned, we're not the first to do this. We were inspired by works of Tobias Brixner, who implemented this type of phase matching condition in 2018. And then there is a small but growing size of publication in this field. Now, as an experimentalist, this sounds a bit tricky, right? 2K1, 2K2, and K3. So you can either do what Tobias did and use pulse shapers, or you can try to do what we did, and this is work in a completely non-collinear geometry. First of all, you save yourself the trouble of shaping artifacts. And second, if you do it fully non-collinear, we can in principle put polarizers in all of these beams and then get even more information out by doing what Donatas mentioned before, so cross-polarization schemes, for example. So how do we get there? How do we get this phase matching condition? Well, first of all, we move away from our beloved square phase matching and go, let's say, back to the triangle, which was more popular in earlier days. And then we realized that both of these, so K1, K2, and K3, and here along the yellow, can come from gratings, right? Now, gratings have different orders, and this was the first order diffraction. If you look at the second order diffraction from this grating, you are just there where you need to be. So this is already this phase matching condition. If you measure here and you use this excitation, these excitation pulses, along this direction, you will get this phase matching condition. So it's not all that hard. If we look at this in the experiment, this is what it looks like. We have a beam splitter. We have something which gives us a T2 delay. We focus into a diffractive optical element. We have something where we look at least 3 orders, 0, +1, +2. And then we have another grating, which basically blocks the 0th order, gives us K1, K2, and wedge pairs. And so if we then look at what we can measure this and this diffraction order, which gives us basically rephasing and non-rephasing at the same time. Or you can look at this diffraction, which gives you the 3rd order and the 5th order. So it's always a good idea to measure 3rd and 5th order at the same time, because these two should have, let's say, phase relations. So it's nice to collect them simultaneously. Okay, so much for the experiment. Now, what type of signals do we expect? We all enjoy double-sided Feynman diagrams, and this is also the language that we use to understand what's going on here. So the simplest system is, of course, a dimer. It's not very practical because Exciton-Exciton Annihilation is going to be extremely fast in dimers. There is no time to migrate through the system. However, it's nice to understand as a starting point, because theoretically it will be the most simple scenario. So we have a ground state, we have one allowed transition, and then we have a doubly excited state. These are all the diagrams you're going to have when looking at dimers. So we have two interactions with K1, which can put you in this FG coherence, which is, this will always be the one that we Fourier transform against. So this is our omega 1. And then we may go back to ground and then go back up again with K3. So then this would be our omega 3. There are many pathways that will lead us to dynamics in the first excited state, this plus state in T2. There are some here, there's some here. Now, the good news is in a dimer, they all cancel. So when you look at the integrated signal, you integrate everything you have in omega 1 and omega 3, then all that remains are these two, right? So these two diagrams are interesting because especially this one is the one that has FF population. So this is what you're after. Now you have a diagram that propagates in a doubly excited state, and this will be the one that will describe your Exciton-Exciton annihilation process. This here is also there, but it's not a problem. First of all, it has a different sign. It's negative, this is positive, and it's only in the ground state. So there is basically no T2 dynamics. So this is very interesting. If this actually works, and it does, then we have something where we can look at dynamics in the doubly excited state, and it comes out with the correct sign in the dimer where all these other things are canceling. So let's put this to a test. Here is a Redfield type of scenario in a dimer. In Redfield, there will be a splitting even between these two peaks. And this is, of course, 2J. This is the measure of the coupling strength. If we then look at the dynamics of these peaks, we will see this P1 decays with a, let's call it convoluted dynamics. This one will have contributions from both the doubly excited manifold and the singly excited manifold. Same is true for P2. However, when you sum them up, you get something that decays mono-exponentially. And this is the simple function it decays with. So yes, it goes, the annihilation rate is the decay constant. So this is good news. In the first regime, it's even easier because now we don't have the splitting between the peaks anymore. The peaks overlap. They have different line shapes. So you still see some positive lobes here at time 0. But basically you have something that decays, and it decays again with the annihilation rate. So with the dimer, everything is good. The dimer, as I said, is not something ideal in an experimental frame because everything will be very fast in the dimer. The next biggest thing is the trimer, and here it's already not so great anymore because what we've changed here are relaxation rates in the first excited manifold down here. So obviously, as you can see here, our integrated signal, so the total peak volume, does change depending on this rate that is active only in the first excited manifold. That's a tricky and interesting point. So the diagrams that I've mentioned to you before, they still cancel. However, what's going on here is that when we put population in this doubly excited state here, it still has now the coupling is very weak, right? So it still has the chance to hop between these sides, no? And this hopping constant is what also contributes here. So the F state does not only decay with the annihilation rate, but it has the chance to still stay in this doubly excited manifold and jump around between these other realizations of a doubly excited manifold. So in the first regime, it's not so nice anymore, but of course it's still solvable because you can measure these rates in this excited state manifold by different means. However, if you go back to a trimer in the Redfield regime, then we have delocalization in our F states. And then we are back to something convenient, because now it doesn't depend anymore on this rate of relaxation in this double excited manifold, because now we are back to our mono-exponential decay. So if we have strong coupling and a trimer, we will still get what we're after. We will still get a mono-exponential decay to our signal in the R5 signal, in the integrated R5 signal, and this decay will be determined by the annihilation rate. So it's still very usable also in a trimeric system. Actually, we can take this a bit further. This will also still look like this if we have a linear homoaggregate. If you have a chain of monomers and they all point in the same direction, it will still look like this in the Redfield regime. Okay, so let's put this to a test, to a real system. That's the last part of the talk. This is the system we were looking at. It's a squarene. Squarene are fantastic systems because they absorb really strongly. They have a humongously big 2-photon cross-section also. And you can form nice aggregates with them. You can also look at trimers like the one we have here. And as you can see, when you make a trimer like this, or you ask Christoph Lambert very nicely to make a trimer like this for you, then you will see that the coupling is fairly strong. This is monomer, dimer, trimer. So what we're looking at is a coupling in the range of 700 wave numbers between the monomers. And all things considered, this puts us safely in the Redfield regime. A bit of a downside, it's floppy. So we will have to consider more than one conformer. And this is where our friends from quantum chemistry come in to calculate the most probable structures for us. And we could make, so we only had to look at 2 structures to get a good view on the entire dynamics. And of course, a trimer is still small enough so that we can use our formal approach and calculate signals in limited time. Now, let's calculate something. Let's look at the absorption spectrum. And so we can look at, we can use our normal Frankel exciton Hamiltonian, and we can use the parameters we get from quantum chemistry, and then we can reproduce the position of the monomeric transition. We can also get the absorption spectrum of the trimer, as you can see. It looks quite nice. And we get these 3 transitions. These are the 3 allowed excitonic transitions. What you can also see is, and this sort of points at the efforts that Maxime put into looking into vibronic things, what you can also see is that here in the middle, we don't quite reach the actual absorption spectrum. And we believe this is because there is a non-negligible vibronic mixing. So yes, there is this vibrational shoulder here in the monomer already, and it's still there in the trimer also. So the mistake that's made here is because of our neglect of vibronic effects. And yes, it would be interesting to go and also get this into the theory, but it's not that straightforward. Okay, so here are the signals. So this is a measured R5 spectrum, and this is a simulated one. This is the energy level scheme that we have. It's a Redfield type of system. And what you can already see is that everything ends, so in omega 1, all signals sort of end up at the same value, both in theory and experiment. And this is, of course, the value of this G alpha, and this is the only coherence that we have in our T1 delay. So this makes a lot of sense. And then there's something else that's interesting. We see 3 separated peaks. And that's because the strongest transition in the trimer will always be from G to A1 and then from A1 to alpha 1. The other ones will be much weaker. And therefore, we have 3 nicely separated transitions. So one talks about this transition from ground to first excited state, then from first to second, and then from second to this final state up there. So because we are already in a Redfield coupling regime, we can just handpick the peaks and look at the dynamics of the manifold we're interested in. And obviously we're interested in that thing up there, the A1 here. So because this, I think that should be alpha. I'm very sorry. Yeah, so this should be alpha. So when we look at this peak up here, these are the only 2 diagrams that we find. So both diagrams have a negative sign, and both diagrams end up in this doubly excited manifold that we're interested in. So this, besides the trimer being already something clearly beyond the dimer system, we can still look at a peak that exclusively talks about dynamics in the doubly excited manifold. Now, I mean, comparing carpets here, experiment and simulation, it's nice, but I mean, there must be many parameters we can use to reproduce this, right? Now, but we can also, we can also look at time traces. So this is the time trace of the integrated 2Q signal up here. So we draw a box around this signal, and then we look at what we see. We see a fast rise, which is due, well, from negative to 0, which is due to Exciton-Exciton annihilation. Let's say this is due to the relaxation out of this alpha manifold to the A manifold. Then, I mean, I'm not going to say we see oscillations because the data quality is not good enough. But in the simulation, when we want to reproduce the absorption spectrum, yes, we should see oscillations out there, which come from this 1300 wave number mode. And then the signal pretty much stays constant. And if we put in 30 femtoseconds annihilation time, we get this type of agreement, which is the best agreement we can have. 25 femtoseconds is already way off. And if we say we don't have annihilation in the system, we get something completely different. So yes, this peak is very sensitive to annihilation dynamics. And I think we have good grounds to argue that we can say that the annihilation rate is in the range of 30 femtoseconds. Now, for the last few minutes, this is something Konstantin is currently working on. So what you can see here is that these peaks are tilted at early times and still also tilted at 55 femtoseconds, while in the simulations, they're pretty much flat. No, they are horizontal. There's no tilt. And we think this is because the lines we were simulating in the slide before are from purely homogeneous line widths. Now, if we start adding static disorder or inhomogeneity, so if we go from a purely Lorentzian profile to this broadened profile, we get this peak shape out. So yes, this tilt is a measure of this type of disorder. And more so, and this is here on my summary slide, even we can say even more than that. We can even talk about if the noise, so to speak, is completely uncorrelated or if it's anti-correlated. The 2Q spectrum, the R5 spectrum will look different. So this will be, and we are currently investigating this, this is an interesting way of talking about correlation between fluctuations on the different sites. Okay, we're already on the summary slide. So I told you why we're interested in Exciton-Exciton annihilation. Then I showed you that R5 spectroscopy, electronic R5 spectroscopy, is a tailor-made and I think very insightful tool to talk about Exciton-Exciton annihilation without the need to do intensity-dependent experiments. And we would like to take this further and test and see if we can also talk about correlations in energy fluctuations of sites and take R5 spectroscopy as a spectroscopic tool for that. I'm closing and I thank you very much.
Thank you very much, Jürgen. So the talk is open for questions. Okay, that's a lot. Let's start with how you're seeing Tom. You didn't ask before.
Oh, I don't think I'm the first one. Someone was before me, but
yeah, please just start. Okay, so I don't see who was first.
Yeah, I just realized that I actually came 1 hour late, so I should say hi to Maxime Gallin first. I missed your talk. I'm sorry. Anyway, thank you, Jürgen. Very nice talk. I just like a quick question about the experimental setup. So I guess you're showing the absorptive spectrum, right? So
that's a very good question. Yes. So let's go back to something that is on the experiment. Sorry for clicking through. Yes. Okay. Yes, I'm showing the absorptive part. And
Okay.
so I'm glad that you bring this up. I was only talking about the advantages of doing it in fully non-collinearly. That's not quite fair, because if you do it partially collinearly, like Tobias did, then you basically work in a pump probe type of geometry, and then you get the absorptive part directly, right?
Right.
Which means
right.
you have to use a shaper and you have to deal with shaping artifacts. These are the downsides. The major upside is that you don't have to face this thing. And this is a real problem because, of course, when you do R3, normal 2D, you face to pump probe. That's already cumbersome. But what you use to face R5 is one level of complication higher. You face to pump dump probe. So you can imagine, you can imagine the strength of the signal that we have to deal with here, right?
Okay.
I mean, another hint is that between R3 and R5, there should always be a phase jump. If you have something purely absorptive in R3, you will have something that will look like a dispersion curve in R5. No? So if they are completely off in this respect, you know that your phasing is wrong. But now at the moment, Max Pinzer and my group is working on rebuilding this experiment. So phasing is so tricky in this that we're not going to go back to this phase matching condition, but we will work in something partially collinear.
Okay, I guess you answered all my question. But okay, so you have to phase to the pump dump and not the 2-photon absorption.
No, it's not a 2-photon. So the projection slice theorem, when you apply it to this, it comes out to pump dump probe. So that makes sense. Yeah.
Okay.
I mean,
Thank
it's just the you know how much weaker the signals get.
Yeah. Thank you.
Okay, I think there's also a question from, sorry if I don't pronounce your name correctly, Arun Shu. Please keep it to one question.
Arun here, yeah.
Please keep it to one question if there's
Sure.
questions as well.
Can I go ahead?
Yeah,
yes.
Please.
Okay. So the question was that in the local basis, in the site basis, you ideally you should start with the 3-level systems, right? And then you kind of build up the basis with the direct product of 3-level systems. To have all the matrix elements that will give you the internal conversion and exciton fusion later. By that argument, the number of 2 exciton states that you get for a trimer, shouldn't it be 6 or something?
But I think it is, no? So
there's 3, right?
No, the trimer level.
So here, for example, in the slide before,
that would be
you got 1 F state. Sorry?
This would be the trimer level scheme that we used here.
Yes, but in the F, I would expect 3 more, right? Let's say, could you please go back 2 slides? Then we can have the same discussion with the dimer. Yes. So in that, I would expect, let's say, 2 more double exciton states. If you start with the coupled 3-level system,
we start. So sorry. We start with coupling 2-level systems.
So this is.
This all comes from 2-level systems.
I saw that.
Paper. Yeah, I only said 3 levels in the very beginning because then I was talking about sites basically.
Yes, but I have a point there actually. Maybe it's a general problem in everything. That the internal conversion, let's say if we, as you know, if we discuss one single site, the internal conversion is basically between 2 and 3, the matrix elements involving those in the upper 2 levels. And if we start with the coupled 2-level system, I don't really see how we can get that matrix element. Maybe in a model, we would recover some of the spectral features, but you see my point, the F and E that you draw the wiggly line, that matrix elements is, it should carry on in a delocalized basis. That was my question.
Yeah, okay, but it doesn't do that, right? So from my as I interpret the literature on this point, it is you are now in this high-lying state, and basically what you put in is a phenomenological decay constant here. I'm not sure how it would come out of a more microscopic picture. But what we measure,
yes, I mean, it can actually, if you, for example,
super fast relaxation from this state in the
so
tens of
Folkert May wrote a paper on the, its probably title is Kinetic Theory of Exciton Annihilation in JChem Phys, I guess, 2015.
The Engel paper, yeah. Mm-hmm.
Yes, and he actually includes that by a Lindblad formalism, and there actually it is there more consistently, I would say.
Okay, I'm sure it is, but I mean, what we are trying to achieve here was we were trying to describe spectroscopic signals, right? So we were modeling our results, and this was, for us, this was basically a fitting parameter. So this doesn't come out of anything more underlying.
Yes, I agree with that.
Okay,
maybe
we should
in the
proceed
diagram.
with thanks. Maybe we should proceed. There's another question from.
I would be happy to get together with my PhD student on this also. No?
Sure, we can. Yeah, I can write an email. Yeah,
fantastic.
So Vivek.
Hi. First of all, thank you for a very interesting talk. So I had two very quick questions. One was, so did you so you mentioned that there are these most probable structures that the electronic structure calculations help you know.
Yes.
My question was, do you expect any dipole interference effects in your in the most probable structure? Like, for example, are the dipoles perpendicular in the
no, they're not. So they are kinked. One is basically straight and slightly kinked, and the other one, I should have a picture somewhere, but I don't want to bring it up. Basically, we don't go to anything that's near orthogonal also.
Okay.
And but we can also, in all structures, we can always exclude interaction between 1 and 3. So it's only nearest neighbor. But this is just what came out of quantum chemistry.
Okay. And I guess a related question was, so you mentioned that there is that GSB contribution that, I guess in the systems you are studying, it's maybe not relevant, but I was just wondering how much does the vibrational relaxation of the ground state contaminate the, extraction of annihilation rate signals?
Okay. Let's look at this again.
I mean, it probably wouldn't be relevant in these systems because of the strong, fast annihilation. But I'm just wondering about.
But I mean, we do see oscillations in the trimer, but there we believe it's basically from the ground state contribution here. Yeah? So they do contribute. They are there, but we cannot explain any fast rise dynamics. So the fast rise will always have to be from the other diagram, which comes from the double excited state again. I wish we had let's say, a setup that would allow us to talk in more detail about the nature of these oscillations, but we didn't do so in any publications because it's a noise argument, no? But we are working on it.
Thank you.
Can I ask a question then, Thomas?
Sure, please do.
Very interesting, Jürgen. I have the following question. So the relaxation of the double excited state is extremely fast, and I guess that everybody agrees with that. Okay, so it goes in something like, well, you said like 30 femtoseconds, right? So that's about the same range. So there are two questions. Okay, the first question is, where does the energy go? And the second question is that this energy is dissipated, right? Finally, which should lead to the local temperature rise.
Absolutely.
Could you please comment on these 2 points?
Where does the energy go? Into the bath. No? The rest will be answered by my good friends in theory. No, but yes, I totally believe that the local temperature will go up. We actually, in a different context, we looked at relaxation in polyenic systems, in carotenoids, and there we saw a sharp increase in local temperature. And if you want to simulate that properly, I think what you would do is you would have even an ND type of approach, where you take the first solvation shell into consideration more explicitly, and then consider your bath basically as anything outside of the first solvation shell. But if you're interested in these local heating effects due to cooling, then you will have to look at something, a more ordered structure around the molecule. So does it affect the R5 signal? Not to the current level of treatment that we have. We still have homogeneous lines, and we're not talking about Markovian, non-Markovian effects in this respect. Maybe we should.
I still am not content with your answer to the first question. Well, of course, everything goes to the bath, right? The question is how it goes to the bath, because it should go that the hell lot of energy, right? So here we're talking about something like 2 electron volts, right? So what would be the intermediate states?
I mean, now we can either talk about this in general, and then we talk about the shape of the spectral density that you put in by talking about the bath structure, or we can talk specifically. And when you talk about it specifically, we would need, I would think, quantum chemistry of high-lying excited states, and this is really tricky. So.
Okay, good, thank you.
Okay. I guess
So,
if there's no
Thomas,
more burning question.
You don't want to ask any questions,
I have not
Thomas?
asked any questions.
Surely you.
I'm here all night. Go on.
I don't think I actually have a good question now.
That's okay.
I will.
Then I can go and celebrate my birthday.
Exactly. Yeah. So maybe a question: how are you going to celebrate it?
Well, in times like these, I bought nice asparagus from a local merchant, and I'm gonna enjoy it with my wife and kids.
And how many kids are you allowed to invite, or the kids are living with you?
But the kids are my kids, so they're allowed to stay.
Oh, right. Okay. Here we have different rules. I mean, for the grown-up kids, okay, it doesn't matter. Only one guest at a time.
Oh, that's really harsh, no?
Well, it's a recommendation.
You follow the rules. Well, so I think with this we should thank Jürgen again and all congratulate him with his birthday, and we will see you 2 weeks from now again.
Oh yeah, absolutely.
So, thanks a lot.
Thank you.
Thank you.